Howdy, my name is Dr. Brian Free, the Principal Investigator for SafePass, an Office of Naval Research Phase 2 SBIR program being performed at Scientific Systems. SafePass, or Safe Encounter Resolution Using Passive Sensors, is a passive perception and collision avoidance system applied to unmanned surface vessels. Before discussing SafePass, I'll give some background on our company. Scientific Systems prides itself on developing autonomous systems across a variety of domains. We are a small business located out of Boston, Massachusetts, focusing on research and development using advanced perception, decision logic, and machine learning algorithms to solve some of our country's most challenging autonomy-related technical problems. Our solutions have been applied to land-based autonomy, unmanned aerial vehicles, maritime systems, including underwater and surface vehicles, and we have a payload on orbit as we speak for a collaborative space-based autonomy mission. Scientific Systems has provided high-quality, cutting-edge autonomy products to our customers for more than 3 decades. You can find out what we've been up to most recently by visiting www.ssci.com. The Navy Challenge. Recent conflicts around the world have highlighted the importance of autonomous platforms, and the Navy is seeking to rapidly increase the size of the unmanned fleet. Small unmanned surface vessels, such as the ones we develop at Scientific Systems, are especially important as they align with the Department of Defense's affordable mass push to produce capable, low-cost platforms at scale. Why manufacture one large, expensive, difficult-to-replace ship when the same resources can provide dozens or hundreds of small, cost-effective, mass-producible platforms with equal or greater mission effectiveness? Naval operations which must be done in emissions-controlled, or EMCON, environments prohibit vessels from using marine radar to detect obstacles in other vessels. For a manned vessel, this means that the crew must use their eyes and ears to keep a safe lookout to avoid collision risks. For unmanned vessels, which often rely entirely on radar, this restricts the USV's capabilities to perceive, track, and avoid other vessels. Until a technology allows these platforms to navigate safely using passive sensors, USVs are not available as assets for the critical Navy missions which occur in EMCON. As we have alluded to, there is no current baseline solution to provide passive tracks on board small USVs. It's true that there exists specialized camera systems such as stereo or multi-camera arrays that can determine distance to nearby vessels, but these are mechanically complex, difficult to source in large numbers, and limited in effective range. For example, a stereo camera's effective range is determined by the distance between the lenses. To range out to the horizon, this distance would become so large that it's mechanically infeasible to hold the two cameras rigid with respect to each other. To reduce platform complexity, a passive ranging system that requires only a single, commercial off-the-shelf monocular camera is desired to enable the Navy's growing fleet of USVs to safely navigate without the use of radar or LiDAR. The SafePass autonomy system was conceived to address these problems. SafePass provides both the passive ranging capability as well as the path planning tools to safely navigate under larger uncertainty of passive tracks. Safe Encounter Resolution Using Passive Sensors, or SafePass, is a marine perception and action system specialized to process monocular camera data to determine range to objects. Let's briefly walk through the diagram seen here to understand how SafePass works. The SafePass pipeline starts with the images captured by the camera. These images are processed by SSCI's Maritime Segmentation and Automatic Target Recognition, or ATR, AI/ML models. These models determine where the horizon line appears in the image and places bounding boxes around objects of interest that may present collision risk. The horizon and bounding box data are then passed to SafePass's 3 passive ranging algorithms, which each produce a range estimate using different physical principle, none of which depend on the size or height of the object. Taking inspiration from history's navigators, SafePass performs passive ranging with a combination of target motion analysis, rate of growth, and statimeter techniques. These 3 independent range estimates are input to the fusion and tracking system, which combines the measurements into a single contact report for each of the nearby vessels. Multi-target tracking is achieved with a sophisticated data association framework that ensures objects which have different visual appearance are not erroneously fused into the same contact report. If a highly accurate track on a specific nearby vessel is desired, SafePass uses closed-loop perception and will produce a target motion analysis maneuver to get a better understanding of the vessel's motion. Changes in the bearing right to the contact throughout OwnShip's maneuver are rich with ranging information. SafePass chooses the maneuver that will best improve the estimate of the contact's position. Finally, when an encounter requires action to avoid collision, SafePass produces a call-regs compliant path to maintain separation and maintain mission. SafePass is sensor and platform agnostic, requiring only a single camera and can be integrated onto a wide variety of platforms and cameras with no additional hardware requirements. Current status. SafePass is nearly complete the base period of this Phase 2 SBIR with ONR. As of June 2025, we have completed the core algorithm development and risk reduction. In addition to our extensive simulation testing, we have done a series of increasingly realistic field tests. In October 2024, we collected sensor data from an onshore deployment of the SafePass system, recording vessels of opportunity entering and exiting Boston Harbor. Offline processing of this sensor data produced tracks that are accurate to within 100 meters of ground truth at 2.5 kilometers and 150 meters at 5 kilometers with no knowledge of contact size, or about 3 to 5% error. In July 2025, we collected sensor data from an on-water deployment on board Scientific Systems Venom USV in the Rhode Island Sound, recording many repetitions of a collision course with a contact vessel. Just recently, in September 2025, we performed a live test of the SafePass system, not just recording sensor data, but processing it live in the field and publishing contact reports live in the field. The system performance was very good, with tracks formed out to 3.4 kilometers with less than 10% ranging error. This test brought our technology to Technology Readiness Level, or TRL 6. With algorithmic refinements based on this test event, offline reprocessing of the data has already brought the ranging error to less than 5%. In our next round of on-water tests, we will show this improved performance live and aim to initiate tracks at the horizon of 5.5 kilometers, bringing this technology to TRL 7. While we have these follow-on series of on-water tests planned for the 2 6-month option periods, they are not currently funded by the Office of Naval Research, and so we are actively seeking the funds we need to bring this product to market. Now let's dive in a bit more to understand some of the core components of SafePass and how they work together to produce the high-quality passive tracks seen in our on-water testing. The first three features are the passive ranging algorithms employed by SafePass. Naval historians will be familiar with the statometer, a physical tool similar to a sextant that can be used to measure visual angles. Sailors can use this visual angle, say 0.3 degrees, together with a known ship height, say 15 meters, and some trigonometry to determine the range to the vessel, about 3 kilometers in this case. SafePass goes through all of these steps for each frame coming off of the sensor, and beyond that does not require a known height of the vessel. While this may seem like a geometrical magic trick, using knowledge of the Earth's curvature, the distance to the horizon from the camera's perspective, and the visual angle between the vessel's waterline and the horizon line is sufficient to calculate range. The second technique, rate of growth, operates not on a single frame, but on a time series of bounding boxes on the same object. The change in position and size of the bounding box is not sufficient to determine range, but it is sufficient to determine if OwnShip and the vessel are on a collision course, and to estimate the time to the closest point of approach. That temporal information is fused into existing spatial tracks to refine the track accuracy when on a potential collision course. The third technique, target motion analysis, is well known by submariners. Target motion analysis, or TMA, estimates range by measuring the change in bearing to the vessel as OwnShip performs a pre-planned zigzag maneuver. SafePass takes this further by selecting the exact zigs and zags on the fly, based on the current track uncertainty. This guarantees that the selected maneuver will be optimal not just for the current encounter geometry, but for the system's current multifaceted understanding of the contact state, allowing multiple hypotheses of contact range to be ruled out until a single high confidence estimate remains. These three techniques are all critically dependent on having a view of the contact in the sensor. For static cameras, the best approach is to combine multiple viewpoints to cover the full 360-degree field of view so that the contact will always be seen. That said, a gimbaled camera with pan, tilt, and zoom controls is preferred to reduce platform complexity and to further extend SafePass's capabilities. SafePass brings the camera to life with scan, find, and follow camera behaviors that integrate tightly with the tracker to ensure all active tracks are updated in a responsible order and that no unknown vessels cross the horizon without a track being formed. Finally, SafePass includes a CallRegs-compliant, uncertainty-aware path planning system to safely resolve encounters while staying on mission. Transition to the fleet. As with all autonomy components at Scientific Systems, SafePass has been designed from the start as a modular set of software artifacts easily deployed to a wide variety of platforms in part or in whole. Because of this, SafePass can be integrated onto both manned and unmanned vessels to provide safe navigation during any operations where the use of active sensors such as radar presents a risk. Though there is utility to deploying to manned vessels, the primary benefit is to bring exquisite capabilities to the off-the-shelf sensors on board low-cost, small USVs. NAVSEA's PMS 406 manages several USV programs that could benefit from the technology and present a possible transition path that we are currently exploring. As the Navy integrates more and more small USVs from various national suppliers, SafePass offers a turnkey solution to enable MCON missions in an otherwise incapable platform. Scientific Systems delivers high-impact software to autonomous platforms in the ground, air, sea, and space domains. Our history of deploying to a wide variety of platforms has required our tools to be flexible to different configurations. For this reason, we are able to provide this technology under three separate business models. First, SafePass can be purchased under a per-unit software license and integrated into platforms with an existing autonomy computer and cameras. Second, SafePass can be purchased as an autonomy-in-a-box embedded computer, which can be integrated onto any platform with a sufficient camera system. And finally, SafePass can be purchased as a hardware bundle, including a capable pan, tilt, and zoom camera. Commercial USV manufacturers can provide an MCON-compatible navigation capability to any current or upcoming platforms with the addition of SafePass software. I appreciate your support and curiosity about our maritime autonomy solutions and would love to talk to you more about your own emerging needs for autonomous systems. You can reach out to me at brian.free@ssci.com or visit our website for more general information. If you are attending Sea, Air, and Space 2026, stop by our booth and I'd be happy to chat in person. Thanks for your time.